So hi guys, sorry for the slightly awkward presentation style, but that's the new world for you. I hope that this talk will be something interesting to the different disciplines we have in the audience. I know we've got a bunch of particle people, a bunch of astro people. Some of you are quite new to machine learning. Some of you are writing NeurIPS and ICML papers. So I've tried to put kind of a mix of everything in. There's a raise your hand feature on Zoom. So just let me know if you've got questions as we go through. And otherwise, I will power on. So I want to start by asking, so what makes machine learning different for physicists? Or to put it more controversially, what are we for? Like, why do we need physicists who are interested in machine learning? If the aim of a lot of computer scientists is to create general purpose learning algorithms, then what does that leave for us to do? Kind of a minimal answer to that question would be, well, we're customers. We take the algorithms that the computer scientists publish, we download them from archive, we download them in Python from pip, we apply them to our problems, we write our papers. And that's a good start, but I think there's a lot more to it. And I think the truth is, it's pretty rare that most of these so-called general purpose algorithms do what we as scientists need them to do. I certainly find it's pretty rare that something will work out of the box for me. And when it does work out of the box, there's a philosophical gap between what it was designed to do and what I as a scientist require. And I think that's because computer science folks are aiming to solve a subtly different problem often. So this is my dog, River, on the left. And I work a lot on classifying galaxies. I'll talk more about that. My question is, what is different about classifying normal data like river, cats and dogs and so on, to classifying physics data like galaxies or your own particle examples? I think the first big thing that's super different is we're often uncertain. We're uncertain about our data. It's often noisy, it's flawed, it's full of artifacts. For astronomers, there are bloody stars in the way. We're often uncertain in our labels. So is this galaxy a spiral galaxy? Well, probably, but I'm not totally sure. And there's no appeal I can go to get that right answer. So we always have some uncertainty in our labels often. And crucially, we also want to be uncertain in our predictions. So CS models are often tested on their accuracy, top 1, top 5. Did the model say that River was a dog? Yes, no. But as scientists, we need to know how sure we can be that this is a spiral galaxy, because good scientific conclusions will require error bars. So in this talk, I want to share with you two things that deep learning, and especially Bayesian deep learning, can do, which I think will be useful for your research as scientists in applying machine learning. And the first big thing is about how to handle uncertainty in your labels and in your predictions. Now, most of the work that I've done so far has been with a group called Galaxy Zoo, a citizen science project classifying galaxies. And that's what I'm going to focus on today. No arrow keys. Okay. So these are the projects which Galaxy Zoo has run to date, starting with GZ2 about a decade ago now almost, up to the current project, Galaxy Zoo Decals, which is the one that I'm leading. Now, in a couple years, we're going to have 2 new big surveys come online, producing a whole bunch of new galaxy images. When LSST comes online, one big survey, we'll need to classify this many galaxies. And when Euclid comes online, space-based telescope, we're going to need to handle this many. Tough. So either we'll have the richest, largest set of morphology measurements to date, or we won't, because we won't be able to keep up. So we have to scale Galaxy Zoo, but we also have to do it right. We have to understand the uncertainty from our volunteers in the quality of their labels. We have to understand the ambiguity in our data, and we have to understand the confidence in our predictions if we want to draw meaningful conclusions. Here is how I built a Bayesian deep learning system to do that. So the first thing we really need is we need our classifier. And here I'm going to be using kind of throughout a pretty standard convolutional neural network, which I expect most of the audience will be familiar with. If you're not, it's a common deep learning image classifier. We're going to make it learn from uncertain labels and make probabilistic predictions. So here's what I mean. So each row here is a galaxy. And my model is predicting for those galaxies posteriors for how many volunteers will say this galaxy has a bar. That's this kind of linear feature you can see. Instead of making kind of just a single, so we think this is a bar, we think this is not, we think it's a dog, we think it's not, we're going to predict a posterior over all the possible things the volunteers might say. How do we do that? Well, the first step is to recognize when you have you ask, n volunteers on Galaxy Zoo, does this galaxy have a bar? And you get back k responses, yes, no. That's a lot like having n trials and k successes. So we're going to model our volunteers as a binomial distribution where we have k people have said bar of n. And so we'll have, in that distribution will be parameterized by what I'm going to call rho, the sort of typical response probability, how likely it is that your average volunteer would say bar. And having sort of framed the problem that way, we can flip it around and we can say, okay, how likely is it that the typical response probability is some number given the data that we've observed? So now we're doing inference. And all we have to do to train our probabilistic convolutional neural network is to treat that log likelihood as the loss. So what we're doing really is we're minimizing our surprise for the typical response probability of each volunteer given the uncertain data we've observed. The k people said this, of n people said that. So that's pretty cool, and that's how we get these posteriors out. So for each k, we know how likely they are. But we're not quite there yet, because what we've made is probabilistic, but not yet Bayesian. And to make it Bayesian, remember kind of the principle of Bayesian statistics in general is to marginalize over the parameters that you're not interested in to find the posteriors for the ones you are. So the catch is we've only trained one model. We could have trained other models given the same data. So we need to marginalize over the parameters of the one CNN that we did train. Unfortunately, we can't do that. It's just not computationally feasible to train many models. The deep learning models are just too expensive. So what we're going to do to work around that is we're going to use dropout. So here's what that looks like. We're going to make many predictions with our forward model, our convolutional neural network for which galaxies have bars. But each time we make a prediction, we're going to permute the network. We're going to turn on and off randomly certain weights within the network. And that will, it approximates training on an ensemble of different models, is one way of looking at it. So while we can't actually train an ensemble of many models, using dropout, we can approximate that effect. So we'll end up with many different predictions for our posteriors. That's these gray traces. And we can then marginalize over those to get our net posterior, if you like. And that posterior can now be any shape. We're not restricted to the binomial distribution shape. And it turns out to be much better calibrated than if you just do a single forward pass probabilistic style. This isn't just a matter of philosophy. Like, you might ask, does it really matter if our predictions are well calibrated, if we can reliably say what's a bar or not? So let me just spend a minute to persuade you why this is important. So often, something that scientists will ask me is, okay, Galaxy Zoo, you guys do a good job at predicting at saying which galaxies are which morphologies, which ones have bars, spiral arms, and so on. But what would an expert scientist say? You know, do you agree with the experts? So here's kind of a little test for our machine learning model. We'd like our whatever machine learning models we train to be able to do the same thing. So I took a sample that had been classified by an expert, Nair, and the expert predictions were similar to the Galaxy Zoo ones, but the expert was a little more sensitive. Now, that's not a big deal. We can kind of calibrate between what the volunteers would say and what the expert would say, given some examples of each. And that's done pretty routinely. The catch is, though, if you use a machine learning model to predict what the volunteers would have said, and then calibrate to what an expert would have said, you get completely the wrong answers out. So here we're trying to say, okay, in this sample of galaxies classified by Nair, how many bars are there? If you use the volunteer predictions with the tweak to make them sensitive like the expert, you get bang on the right answer. But if you use the machine learning model, you get very wrong counts for how many barred galaxies there are, right? One of the most simple measurements you might try and make for a population of galaxies. Why is that? It's because the convolutional neural networks, as people usually train them, are extremely overconfident when you look at a large sample. So the mapping between what the normal neural network would predict and what the volunteers would predict, they usually agree, but they're very different confidences. The network is usually overconfident. But when you use the Bayesian approach that I just kind of outlined, where you take instead your sort of binomial model for what the volunteers would say, and when you marginalize over the different networks you might train with dropout, you get, again, bang on the right number of answers, the right number of bars in the galaxy sample. So if you're a scientist and you're trying to say something about what environmental conditions around galaxies causes bars, are they caused by mergers, etc., it's really important that you can trust the confidence in the predictions of your machine learning model. That's the first half of what I've been working on, about how we handle uncertainty and why uncertainty is important for science. And I think that this will be familiar to some people from previous talks. So what I want to spend more time on is, where do we go from there? Okay. And the motivation is, well, another thing that makes machine learning different for us as physicists is that we're free. What do I mean? Well, computer scientists are often trying to develop excellent general purpose algorithms with really good inductive biases so that they can learn very well on some set of data. But that set of data is almost always fixed. Say it's ImageNet. And that has to be the case because what they're kind of comparing is the design of the algorithm. And that's the variable that they're trying to change. But us as physicists, the algorithm is more incidental. What we want is the answers. What we want is the answers so we can do science. So we have a freedom then to change not only the algorithm we're using, but also the data we're collecting. I think that sometimes we can fall into a bit of a trap where reading a lot of computer science blogs and papers and so on, we can inherit that kind of CS mindset. And I think it's really important to break free of that for both astro and particle folks. Here, we can use that freedom to select which galaxies we think will be most informative for training our model. And that's called active learning. And it will be an effective tool where the data you have has not yet been collected, perhaps is expensive by some metric to collect, or where you have some cost other than literal expense to collect. Okay, so we need some different components to do active learning. The gist of it will be, we have our pile of subjects to label, and we have our model, and we've labeled a few random ones to start with. We want to know which subjects should I choose that will help me train the best possible model? And I can then use that best possible model to make predictions on, the very large number of things that I could never feasibly label. That's the regime that Astro is often in. It's certainly true for Galaxy Zoo, where we have LSSC and Euclid turning on. I suspect it's true of Particle as well in many cases. So we need some principles to choose what to label. And people choose different ways of doing this. But here's one I really like. This is not my derivation, but I think it's super interesting. So you need to know two things for this. One you can argue with, one you can't. The first thing you want to know is the definition for the mutual information, which you can think of as how much information one variable carries about another. If I know the value of X, how much do I therefore know about the value of Y? And that relates to the entropes in those random variables. And this definition is pretty much straight out of Shannon. The fixed law of the land. Second component we're going to need is some definition for what does it mean to know more about something, right? How do we quantify the information gain from acquiring a label and training our model better? Here's I think, a common and intuitive way of doing that. So we're going to look at the expected entropy decrease in the parameters of our model having acquired this label. So the first term here is the entropy over the parameters in our model minus how much entropy we expect to have after we've acquired our new label for our new subject. So here, X would be my galaxy, and Y would be the label from the volunteer. So it turns out this information gain, while kind of pleasant way to express it, is actually really hard to calculate because we don't know the probability of the parameters within our model, and we definitely don't know their entropy. We've only kind of trained one model. But by symmetry, because the mutual information is symmetric, we can rewrite this as the mutual information, flip it around, and expand it back out. And what we get now is the information gain as the entropy in the expected label, so the predicted label that we'll get from our model, our posterior, minus the posterior that we'll have per each model. And these are now things that we actually know, right? Because we've just done all this work to find our posteriors for the labels given some galaxy picture. So we know these guys. I don't know if you can see my mouse, hopefully. And we can pretend that we know the value, this kind of expectation over different models using dropout. We can approximate that. So for the specific case of Galaxy Zoo, we're going to be picking galaxies where the models confidently disagree. So where the entropy in the predictions for each galaxy, for each model is quite low, but the entropy over many models is quite high. In other words, each model is confident, narrow posterior, but they give different answers, wide posterior over all of them, that green line. And we can only do that because we thought about the labels probabilistically, and because we approximated training many models in our kind of Bayesian framework with dropout. Here's what happens running this in practice. So if we simulate running, collecting more galaxies with, this is with Galaxy Zoo 2 data, we compare selecting the next galaxies to learn from either randomly, that's our baseline in orange, or by our mutual information acquisition function in blue. We're reaching kind of the same levels of performance. This is error on the y-axis, so lower is better. So we're performing better, much better, after, this is like 50% better, after far fewer galaxies. Or to put it another way, we get to the same level of performance having acquired half as many galaxies. We're getting more galaxies as we go this way. So what that means is we can train better models faster and therefore give astronomers the morphology predictions that they would like to use. You might ask, all right, so which galaxies are actually informative? Here's what happens if you train a model to classify if a galaxy is smooth, like a blob, or featured, like disk, spiral arm, this kind of thing. It turns out that it very much matches kind of what your intuition might say. So galaxies which are helpful for training the model are galaxies which are kind of interesting and diverse and have some features. But galaxies which are not helpful for training the model are kind of boring, they're blobs. We'd expect that nearly any model would do a good job of classifying these guys. You wouldn't need to see tens of thousands, hundreds of thousands of these to say, yeah, that's probably a blob. Apologies to the people who study elliptical galaxies. We can kind of quantify this as well. So it turns out that these, in Galaxy Zoo 2 anyway, elliptical galaxies are super common. This is how elliptical you are, how smooth you are. And by far the dominant class, if you like, is galaxies which are highly smooth. But once you pick galaxies with the mutual information function, we massively smooth that out. And in fact, the model prefers featured galaxies so strongly, we end up with a slight preference towards featured galaxies. We can ask the same kind of question, which galaxies are informative, if I would train a model to predict which galaxies have a bar. This one is a bit less obvious. I took a long time squinting at it to work it out. You might be quicker than me. The difference, I think, is in the resolution, right? So the galaxies on the right-hand side that aren't informative are kind of blurry, they're blobby. You can't really see if they have a bar or not. But the galaxies on the left-hand side, the centers are well resolved. You can see, okay, yes, this has a bar. No, this doesn't have a bar. And we can verify that again quantitatively. Well, the resolution of the picture, if you like, is going to be a very good proxy of the redshift, right? Galaxies that are further away will be less well resolved. And indeed, galaxies selected randomly are at higher redshifts than galaxies selected with active learning. And these low redshift galaxies are more informative for teaching the model what is a bar and what is not. It's really important to say, just before I move on, that it's not something I programmed into the model to do that. It's just something which follows from the mathematics of how we set it up. The model finds those galaxies to be helpful, and it's only after the fact they're looking at, oh yeah, I guess that does make sense. The low redshift ones are useful. So if you're using this kind of mathematical framework, whether an aster or particle or whatever problem, that should hopefully be helpful to you. This is where I move into the latest and greatest stuff. I haven't given this part of a talk before. I'm kind of curious to see what you guys think of it. I'd love to hear afterwards. It turns out that as we run active learning on Galaxy Zoo, and we've had it running live for a while, and it's been quite effective for us, there's a bit of a practical catch where we don't want to have to train a different model to answer each question, right? I don't want to have to, tell my collaboration, oh, we need to spend 3 months optimizing for smooth versus featured galaxies, and then another 3 months doing barred galaxies versus unbarred galaxies. It feels very inefficient. It feels like we should be able to design a model which, firstly, can answer all of the questions at once, and secondly, we can optimize its performance over all of those questions at the same time. In other words, what we're going to try and do is say which galaxies would be most informative for learning about all of morphology, all the questions we'd like to answer, and not just one particular question at a time. Luckily, kind of with the math in place from before, this is fairly straightforward. So the first big change we're going to do is, instead of having our model predict the typical probability that a volunteer will say smooth or featured, we're going to have it predict the vector for every galaxy. And the length of the vector will be the number of answers we want it to predict. It's quite classic kind of setup for multi-class classification. But we're going to interpret each element in that vector as the probability of that answer. We know that within questions, all the answers, or the probability of all the answers have to add up to 1. So we'll softmax between questions to make sure that probability that it's, say, smooth yes plus smooth no equals 1, bar strong plus bar weak plus bar no equals 1, etc. And having done that, we can just repeat the same log likelihood trick as before, right? Where we interpret these as our typical response probabilities. And now we're going to take the product of the log likelihood of getting the observed data over all the questions, right? So we're saying, given the questions are independent, what's the odds of getting the right predictions for all of them? And we're minimizing our surprise on that. Crucially, this not only lets us predict for all the answers at once, but it frees us from doing binary questions as well. So here I'm subtly changing from saying bar, yes, it's barred, no, it's not, to does it have a strong bar, does it have a weak bar, or does it have no bar? And that's going to be useful, I hope, for people who are interested in how bars form, say, because the strong and weak bars may have different mechanisms that cause them. So it's important that we can make more refined judgments about detailed morphology at a scale which is not possible with humans alone, but is possible supported by citizen science. So here's kind of the latest version of the plot I showed you guys before, where we show our posteriors. Now again, we have galaxies in the rows, but we have every column is a particular answer in the galaxy zoo decision tree. So it's obviously too small to really see, but this is like smooth, featured, spiral arms, yes, spiral arms, no, etc. And again, we have our dropout, our sort of single forward passes in gray. And then we have the marginalized predictions when we run dropout many times and average over those gray ones in green. And this is, I should say, a random set of galaxies. So this is totally representative of the typical performance of the model. And you can see it does a pretty strong job at predicting, at the very least, what the volunteers really said. So these posteriors are, again, well calibrated. And what I found really fascinating in this is it turns out that if you train a model to predict all the tasks at once, all the answers, it does better than if you trained a model to predict specifically one question only. So if I train a model to say, how many spiral arms does this galaxy have? And I, as usual, and that's the only question I'm trying to answer, it'll have some had some performance. But as I tell a model, okay, predicts how many spiral arms you have, is this galaxy featured, does it have spiral arms, does it have a bar, etc. It does very substantially better than the model trained only on one question. And this is quite a well-known CS effect called multitask learning. And I think intuitive, it makes sense because knowing what a spiral arm is helps you answer how many there are, right? Knowing what a featured galaxy is helps you answer, is this a spiral arm or not? Like the questions are not independent. If you understand what some of them are, some answers are, you'll also understand what others are. And just to bring it a little bit away from the somewhat dry, useful but dry posteriors, here are some more random examples of galaxy predictions. So these are galaxies the model is confident do not have bars. This is galaxies the model is confident have weak bars. You see these small bars. And this is galaxies the model is confident has strong bars. So for a more intuitive kind of performance measurement, this is at the level which astronomers would find useful for selecting samples. And notice that we've gone from binary questions to questions with as many answers as we like. And we can also, of course, combine them, right? So I might want to select a sample like the one on the left, where I've said, give me all the galaxies with strong bars, but no spiral arms, or on the right, galaxies with strong bars, but and spiral arms. So it's kind of choose your own sample with the same model. The last piece of the puzzle then, we've built a model which can handle our uncertain labels, which can make posteriors over all the questions at once. And we have some acquisition function for saying, okay, what do we think is informative? We just need to generalize that to the multi-question setup. So what do we mean by informative over many questions? Well, we already had, if we're trying to answer one question, I showed you how we calculate the mutual information that we expect for answering that from the disagreement in the models. Remember that models which are individually confident but disagree, the galaxies where the models are individually confident but disagree are likely to be the most informative. To generalize that to multi-question, all we have to do is consider again the conditional probabilities. So how useful would it be, how much information would we gain, let's say, for labeling a spiral, for labeling a particular galaxy and asking, is it spiral or not? Well, we know how much information we'd gain if that was the only question. That's what we already calculated before. So we just multiply that through by the probability the question will actually be asked, right? If the question isn't asked, we can't gain any information. Luckily, we know that probability. It's simply going to be the prediction for the answer which leads to that question. So if I want to know how informative it would be for asking if a galaxy has spiral arms or not, it's simply the information gain given that I asked, does this galaxy have spiral arms, multiplied by the probability that a volunteer will complete the featured answer to the previous question that would lead them to spiral in the first place. And of course, you can recurse, right? So for however many conditional levels you want, you just ask the probability for all the previous answers. And here are the galaxies which we find informative across all the questions for predicting all the answers. So whereas before we had that clear separation of featured or not featured, well-resolved, not well-resolved, the galaxies that we find are informative across all the questions are galaxies that have, I would say, distinctly unusual but not completely wacky morphologies. So galaxies which are resolved, you can see a lot of interesting structure, but that have structure which is kind of reminiscent of things you would expect. You know, you can kind of see spiral arms and cores and so on, but that are different in their own kind of unique way. And I think that that again matches our kind of intuition for what would be useful. The model is able to classify the obvious smooth stuff easily. It's able to classify the obvious featured stuff easily, the obvious spiral arms, the obvious bars. And what it finds helpful and useful for the humans to label is the stuff that's kind of in the middle, the stuff that's a little bit different to what the rest of the sample has. This is sort of really recent results, like a day or two ago. So we're still trying to work out, you know, how do we quantify this better? What does it mean? Is it robust? But it seems promising. Lastly, we can just look at how much then does each individual question contribute to how informative a galaxy is, right? Because we've done those conditional, how informative it is for each question, and kind of added them up and picked the galaxies most informative over all the questions, we can break it apart and say, okay, how helpful is this galaxy for answering, is it smooth or featured? How helpful is this galaxy for answering, does it have spiral arms or not? And we find that the most helpful, the questions which are most important for picking informative galaxies are the questions which are the hardest to answer, I would say. So the questions where the model performs worse, which is finding spiral arms, finding bars, relatively speaking, are much more likely to be selected than questions where the model kind of already has it covered. You know, saying if a galaxy is smooth or featured, saying if it has a big bulge or not, are relatively simple questions by eye and are relatively simple questions by the performance metrics of the model. I'm really happy to say that we've been running Active Learning live on Galaxy Zoo for a while now with the binary setup, so optimizing individual questions. We're excited to finish generalizing that to multi-questions and multi-answers so that our volunteers can be even more effective in helping us train good models, and that we can then use those good models to classify the next generation of surveys, which astronomers will need to answer the next generation of questions about how galaxies evolve. There's so much stuff we don't know about the relation between the morphology and the underlying kind of physics and kinematics and history that the morphology traces. And having these large samples with statistically robust posteriors, I hope will be a really valuable tool for scientists to answer that. Thank you very much for your time. And now I hope I haven't been muted the whole time.
Thanks, Mike. So does anyone have questions on this? Then now is the time. Please go ahead.
I have a question.
Yeah, please go ahead.
So you're using active learning to figure out which galaxies are most informative, and that's awesome. Are there any risks of sort of a mode collapse, or like if your model is just poorly trained in some area and it gives you the wrong acquisition function?
Yeah, it's a great question. I think we minimize that risk by the design of our acquisition function. I think that I think some of those mode collapses are because no matter how many examples you label in that mode, the model will not learn from those kinds of examples. I think that's often caused by acquisition functions around uncertainty directly. Like if you're trying to predict, the outcome of a coin toss, you're never going to do a good job at learning to do that. So you'll just keep hitting that mode. I think that by using our sort of confident disagreement, it's called Bayesian active learning by disagreement selection function, we'll minimize that risk. I do think it's something we have to watch out for. And I think the classic difficulty in active learning is once you've labeled the stuff, you can't unlabel it, right? So we need to proceed carefully in monitoring our performance as we gather more galaxies. And something we're doing the second time around with the multi-question is being much more rigorous in testing offline, simulating running active learning and showing that this really works before we go live. So we should empirically know beforehand, at least to some degree. It's definitely worth worrying about.
Great, thank you.
Yeah, so if anyone does have a question, then now is the time to speak. If not, then I guess we can thank Mike by either unmuting and clapping, or I think there's a virtual clap as well if you click on reactions on top bottom. So I'm definitely gonna clap this way. There you go.
All right. Cheers, guys.